Okay, well, good morning. I'm going to be talking today about the Ballerina programming language. So the object of the presentation is to give you a description of Ballerina. The particular version of Ballerina I'm describing is the version that's in the process of being released. We got an alpha, so it's a 2021 version, and there are quite a lot of differences between this and the earlier version. I'm going to try and cover all the significant features of the language, but I'm not going to talk about the platform. Ballerina is not just a language, but it's a complete platform with things like testing, documentation, a package system, things like that. I'm not going to talk about that. I'm just going to talk about the language, and I'm going to assume that you have some experience with programming languages, particularly have some experience with a C family language like C, C++, TypeScript, JavaScript. I'm also going to assume you have you know what static typing is. So you haven't just had JavaScript, for example, which just does static typing. If you had TypeScript by itself, that will be enough. So the other source of information about the language, one of the other sources of information about the language is the language specification. But that is more of a concise record of the language design. And it's a lot more, it tries to be precise and detailed rather than being easy to understand. So that's quite hard going. If you want to try and learn the language just by looking at the language specification, that would be quite hard going. But I think after you've had this presentation, hopefully you should be able to look at that and understand it a bit better. So we've got I've decided to divide the presentation into three parts. First part is about the sort of basic functionality that all languages have to provide. So, all languages have, have ints and they have Booleans and you have loops and you have conditionals, all that sort of thing. Everybody has to provide that somehow, but it's not particularly interesting. And Ballerina isn't trying to be innovative here, but you do need this stuff. You need the basics. You need to be able to have a condition and a loop in order to be able to use the interesting stuff. So the first part is going to talk about these sort of a minimal, just enough about the basics that you've got a foundation to understand the interesting bit, which is what part 2 is about. And then part 3 circles back to give a little bit more depth about part 1, which is interesting to know, but it's not the point of Ballerina. So I'm going to start with part 1. And really what I'm going to be doing here is describing a subset of the language, a subset of Ballerina that is designed to have a lot in common with widely used popular language today, which are based on C. So C, C++, Java, C#, TypeScript, JavaScript. They're all C family, what you might call C family languages. And they all have an awful lot in common. How you do if, the overall syntax, there's a lot in common. If you know one of them, then you're quite far along. You can get started with all the others quite easily. And Ballerina is designed to take advantage of that. If you know one of these, then it's similarly easy. It should be similarly easy to get started with Ballerina. So part one, what I'm doing is describing a subset of Ballerina that should feel very familiar if you are familiar with one of the languages I've mentioned. This subset is not of itself interesting. If that was all there was in Ballerina, Ballerina would not be interesting. But it's the foundation on which that you need in order to be able to start using some of the more distinctive features that we'll get to in part 2. And I think it's important to understand this subset because if you try and master all of Ballerina in one go, there's a lot there and it's quite complicated. But actually, you don't need to understand all of it in order to start doing useful things in Ballerina. Okay, so let's get started. So we'll start at the top. Ballerina program consists of modules. Modules can have multiple files. We use the extension .bal. And the most important thing that a module does is to define functions. But typically, any program well, typically any program that does something useful is going to need to import library functions. And let me just see if I can figure out how to make this highlighting work. I think I can do this. Now, you should be, do you see a little red dot somewhere on my screen sharing thing? Yes, yes, good. Okay, great. So this line here is importing, making available a library module. And our library modules have two-part names as far as the program is concerned. They have an organization, which here is Ballerina, and they have the module name, which is IO. And when you do an import like this, you can then access the function using a prefix. And the prefix by default comes from the last part of the module name. So this is importing the IO module from the Ballerina organization, and then we're calling the printline function in the IO module. Now in Ballerina, whenever you see, whenever you want to use a function in another module, you always explicitly prefix it with the prefix that you use to import that module, or rather the prefix that was assigned by the import statement that imports the module. And here we have a main function. So you always learn a lot from a hello world program. So we've got a main function. This is the entry point. It's public because it's called from outside. And we're using curly braces, just like in C. And there's a function, and inside we've got a statement, which is a function call, which calls this function with an argument. Okay, so far. So I'm hoping that everything in part one should be pretty straightforward. Okay. Okay, so functions. We've seen one function. Here's another function. This function has parameters. Here we are defining two parameters, and we're giving the type of the parameters, which are int in this case, and it's returning an int. And the way, so the parameter syntax is just like C or C++. We get the list of parameter names and their types, and we have the returns clause in the function declaration that tells you what it returns instead of putting it in the front like C does. And we have the type, our return, we have types, we have static types, so we're saying that add always returns an int, and its arguments are int and int. And here we're assigning, we have a variable called sum, type int, to which we are assigning, we're adding, have an expression that adds x and y, and assigns the result to sum, and then we're returning sum. We now need to talk about, let's talk a little bit about variables and types. So, so here we are importing the IO again. We're declaring a variable greeting of type string, and we're initializing it to hello. So variables have types, and there's a built-in set of name types: int, float, string, Boolean. And here we are assigning a local, but we can have module level variables and we can have local variables. And here we are defining a local variable of type string, and we are assigning it the value, sorry, a local variable type string name, and we are assigning it the value James. One thing to note here is that unlike C and C++, our assignments are statements and not expressions, so you can't do the if x equals y equals not thing that you see in C. Okay, so this now makes a little bit more sense. We can define parameters to have types, and this is how you do functions I talked about just earlier. Okay, so syntax. Comments start with double slash, go to the end of the line, which comes from C++. Module, things at the module level, syntactically, they either have curly braces or they end with a semicolon. And unlike in JavaScript, you can't omit semicolons, you need to put the semicolon in. Our identifier syntax is like C. Keywords are reserved. If you need to use a reserved keyword for whatever reason as an identifier, you can put a single quote in front of it. And we support Unicode. So Here's a little time name as a Unicode function. Here's another one. And you have a couple of different ways of escaping Unicode in order to use it in identifiers. You can put the code point \u curly braces. This is JavaScript escape syntax. But overall, the syntax is the syntactic form is very C-like. Okay, so we have a bunch of types, and pretty much all these languages I talked about, they have an integer type. Our integer type is called int, and it's 64-bit. So it's the same as long in Java. Integer literals, they can be, by default, they're decimal, but you can have hex, have them in hex too. We don't have octal. We have the usual arithmetic operations, same as C. Operator precedence exactly as in C, which is the same as Java, which is the same as JavaScript, all the same. We don't have increment and decrement, so we don't have double plus, double minus. We do have compound assignment. And one thing where we are different from quite a lot of languages is that overflow is an error. Overflow will result in a runtime error. So we don't just wrap around and give you the wrong result. And we have the usual comparison operators. So ints work pretty much like you'd expect. We also have floats, and our floats are IEEE 64-bit, so same as double in Java, same operators as int. And we don't have implicit conversions between float and int. If you want to convert, you need to be explicit about it. And this is a general thing in Ballerina, that we try to make code emphasize ease of maintenance, ease of understanding, over making it super easy to write. We want codes maintained and read over a long period of years. And having super clever code that's very concise and has lots of clever tricks in it doesn't make for a good maintenance experience. And if you want to convert, you can use the type name in angle brackets here. And floats work pretty much the same as you'd expect. The only thing where we're slightly different from a lot of languages is nan. I don't know if people know what nan is. It's an IEEE value that is not a number. And in a lot of languages, nan is not equal to itself. So if you go nan equals nan in Java, it will be false, which may be surprising to you. Anyway, so we don't do that. Our equals is it the same value? And that's not the same as the IEEE, which is a numerical equals operation. Anyways, that's just something to be aware of if you know other languages. But I don't think it's something that will surprise people who are new to this. Okay, so we have int, we have float, now we have Boolean. So Boolean is what you expect. We've got two values, true and false. And our conditional expressions work like C. You've got expressions with the 3-operand question mark colon thing. And then we've got if else, just as in C. The only difference with RSLs is braces are not optional. So you have to put the braces here. You can't leave them off. But you don't have to put the parentheses around here. There's no need for parentheses here and here because you've got curly braces showing you where things start. So Booleans, it has the not operator. We have the and or operators, and they work just as in C, though, so they don't evaluate the second operand if you know the answer already from the first operand. So that's all, nothing surprising here at all. I think we don't have implicit conversions between int and Boolean, but I don't think there's anything surprising here. Okay, nil. Nil's a little bit more interesting. So this is our version of null, and we call it nil, and we write it with empty parentheses. And it's a little bit, the reason we don't call it null is it's quite a bit different from the C family null. First big difference is that types do not implicitly allow nil. If I say this is a string, it can't be nil. If it's a string, it's a string. It doesn't allow nil. If you want to allow a string or an int or nil, then you can use this question mark operator. So int question mark v means that v is either an int or it's nil. So that's the first big difference. And that means you don't get null, that means the type system catches null pointer exceptions for you. The other big difference is that our nil type also does what other languages do with void. So if you have a function declaration like this that doesn't specify a return type, it actually returns nil, returns a value, and leaving off the return value means return nil. And when you fall off the end of the function using return or just the control flow going to the end, that returns nil. And we don't have a void type, so we have nil does both these things. And this is actually like, if you're familiar with ML, this is how things work in ML. Strings. So our strings are Unicode, they're immutable. They're not objects, they don't have an identity. All there is to a string is the characters it contains. So it works a bit like JavaScript strings. String literals work basically as in JavaScript. We have the usual Unicode escapes. You can put Unicode characters in with the code point here. Concatenation uses plus. There's no separate character type. Characters are, just as in JavaScript, characters are represented by strings of length 1. You can index into strings. You can index, and that's indexed based on the character. So if I index into greeting, first character is H, second is E, second is L, second is O. So I index into hello. I ask for character index 0, I'll get a 0 length string representing the character, the first character. And we also support comparison operators on strings, and those use the Unicode code points. So they will give you an order, which is okay for ASCII, but if you start doing Unicode comparisons, it's not going to give the order that various languages and cultures expect for comparison. So we also have this concept of, so I talked earlier about the fact that Ballerina was a complete platform with an extensive set of libraries. There's also a core library, which we call langlib, which provides the basic operations on the data types that the Ballerina language provides. So the Ballerina language has this string data type, and so we have a module that provides operations on strings, like substring, for example. And that module is called lang.string. And we have a special little feature which allows you to, instead of having to import the string and then call it explicitly, you can use a method-like syntax here. So if I do a very important method is give me the length of the string, you call that with s.length, and that is exactly the same as calling this function in the string here is by default bound to the lang.string module, and this is calling the length function in the lang.string module with the s argument. But instead of saying that, you can say this more conveniently like this. So there are a whole bunch of these, so int and float and string, they all have a bunch of different useful functions, which I'm not going to describe. You can look in they all have documentation. But I think it's important to understand that these are not, even though you can use this method-like syntax, they're not objects. Ballerina is not an object-oriented language. This is just a convenient syntax for accessing these very common methods of built-in types, but they're not objects. So we talked about a bunch about simple types that aren't made up of other types, values that aren't made up of other types. Now let's have a look at how you can have compound data types where you're building up values from other values. So the simplest of these is arrays. So this here is just like the C syntax. This is an array of ints. This type here is an array of ints. So we're declaring variable v to an array of ints. And then we're using this syntax here to construct an array of ints. So our constructor syntax is just like JSON. It's like JavaScript too, I think. And then we index into it using square brackets, and you're getting an array of length 3. So just like with lang.string, there are various functions you can call, including length, to perform various primitive operations on arrays. And we also have ordering. And ordering is based on, it's like ordering of strings, it's based on lexicographical ordering, comparing the members. So one thing where we are different, quite a bit different, I think, from most languages, is that our equals, equals, and not equals is not saying, does it refer to the same, is it the same place in memory? It's, does it have the same value? So if I have two arrays, which I've constructed at different times, they're distinct arrays in that I can mutate one and that won't affect the other. But what equals, equals do, it doesn't test whether they are in the same place in memory. It tests whether they have the same contents. So equals, equals is a deep comparison operator on the values, on the members of the array. Arrays are equal if they have the same members in the same order. And ordering, yes, ordering then is a generalization of that. Okay, so if you have arrays, we want to iterate over them, and there are two ways we can iterate over arrays. One is, and these both use the for each keyword. One is you can iterate over each member. So here we're iterating over an array, and we're adding it up. So this for each type in array binds X successively to each member of the array and executes what's in curly brackets. So it's a bit like, it's like for each in C sharp, actually. So that's the easy way if you just want to get each member of the array in turn. But sometimes you want to access arrays by getting each index in the array. And you can do this by using this construct. So this construct here creates you, if it's similar to creating a list of, so this syntax here is a range operator, which comes from Swift, in fact. So this gives you it's very similar to giving a list of all the indexes of the array, and then you iterate over all the indexes of the array, but it doesn't actually concretely construct the array. So you can think of this as creating a list of all the indices, all the valid indices of the array, and then we're iterating over it. So you can iterate in a traditional C style, or you can iterate in a slightly more succinct style here, but this doesn't always do what you want. Sometimes you want to refer to other indices, or if you want to mutate the arrays, often you'll need the index to be able to do something. As well as for each, we have while, which works exactly as in C, C++. We've got the usual break and continue statements. Here's a little example that gives me the length of a linked list, and we just iterate over the linked list. And so while is completely unsurprising. Okay, binary data. We represent binary data as an array of bytes. What's a byte? A byte is actually an integer in the range 0 to 255. So it's not a separate, it's a subtype of int. This is a little bit different from how things work in most C family languages. So byte, if we have a char type in C, it's not a subtype of int, it's a completely separate type. But our worldview is that byte is a subtype of int, it's just saying an int where you've got a collection. Our int has 2 to the 64 values, and we're saying that the valid values are the 256 values between 0 and 255. And so we know about arrays, you know about bytes. We also have the normal bitwise operations, same as in Java or C. So Java adds I always forget which way around it is, the signed or the unsigned right shift. There are 2 flavors of right shift anyway. So we have both flavors. And we know the typing knows the obvious things. So if you take an int and you AND it with a byte, so if you take an int and you take something in the range 0 to 255 and you do bitwise AND, you know just from maths that that is going to be in the range 0 to 255. And so we can make that be a byte here. But it's not a separate type. That is important understand. And that is different from a lot of languages. Okay, so apart from arrays, the other type we have is maps. The other, well, we actually have more than that, but we also have maps. The map syntax has the type in arguments between curly brackets here. So this is a map of ints. Our keys in maps are strings. So this means it's like an object it's like a map in JSON or an object in JSON, where the keys are strings and the values are ints. And the syntax is JSON syntax. You can use JSON syntax, and that's valid map syntax. So this here, we're looking up where we can use square brackets to index into a map, and if it's not there, you'll get a nil. So the type here has to be in question mark, not int. And we can assign, again, also using square brackets. Now note that if you want to assign one value to another, you can't just do mx here. It wouldn't use, if you try to use this here, you get a type error because the type of this is in question mark, but the type of the map holds ints and not nils. So this would be an error. There's a lang-lib function. If you know, for whatever reason, that you have a key called x, then you can get it and the type will be int. And if it's not there, you'll get a runtime error. So we don't allow, you've got to say decide what you mean and say it. You can't just sweep nulls under the carpet and hope they don't cause you a problem. You've got to be explicit about it. Okay, so let's talk about defining types. So we've seen a bunch of types. You can define your own types. So here we're defining a type called map array, and that is an array of maps, and they're maps whose values are strings. So type here is just like type def in C or C++. It's just saying this name here is equivalent to this type descriptor here. And if we define a type like this, then we can use it like our built-in types. And here we have an array of maps. We also have a record type. Now, record type is a bit different in that with a map, you don't get to control what your keys are. A map, you can have any string. Whereas with record, we're saying we've got these specific keys. So here we have a record with keys X and Y. And this is the record type. So saying R is this record type, and we're initializing it to, we're using names without quotes here. But typically when you're doing this, you would use a type definition. So here we are defining a type coord, which is this same record type, and then we can initialize it to using a record constructor here. And we can then, when you're accessing it, because we know the compiler will check for us, the compiler says you must have an X and a Y, we can use .x here, and we know that that's an int because we've declared it to be a coord, and we know that coord has an X. So that here is compile time guaranteed not to produce a nil. Okay. So talk a little bit about typing in Ballerina. The kind of typing you have in Ballerina is called structural typing. So typing in Ballerina is structural. So when you think of a type, what is a type? It's basically a set of values. And one type is a subtype of another type if the set of values allowed by one type is a subset of the set of values allowed by another other type. So byte allows a subset of, so int has 2 to the 64 values. Byte allows, is a type that allows 256 of those values. and all the values that byte allows are allowed by int. So the set of values allowed by byte, a subset of the set of values allowed by int, so byte is a subtype of int. So we have our, if you think of our universe of all the possible values, we divide them into what we call basic types. So nil and true and false are different values. Nil is a distinct value from true, true is a distinct value from false, and true is a distinct value from 1 or 0. And 1 is a different value from integer 1 is a different value from float 1. So every value belongs to exactly one basic type. You can think of the value as being tagged with its type. So of the basic values, basic types we've seen so far, some are immutable. We have nil, Boolean, int, float, string. And we've also seen a couple of mutable basic types. We've seen array, and we've seen map and record. An important thing to understand, I think, is that every value belongs to exactly one of these basic types. It doesn't belong to exactly one type, but it does exactly belong to one basic type. Now, the story that I've told you about types being set of values, that will get you 90% of the way there, but it's a little bit more complicated when we come to mutability. But if you think about types being set of values, you will understand how typing works and when one type is a subtype of another. Well, now we understand what structural typing is, we can talk about unions. We've actually already seen a very simple kind of union, which is T question mark. T question mark means exactly the same thing as T or nil. It means the set of values allowed by T question mark is the set of values allowed by T or nil. But we have this in a more general form. You can say, if you have two types, you can say T1 or T2 to mean the union of those two types. So here we have, we're defining a record type structured name, and we're saying that the name type is either a structured name or it's a string. And if we now have this name and we want to turn it into a string, okay, we can say the two possibilities. The name may be a string, in which case we don't have to do anything, or it may be a structured name, in which case we're going to turn it into a string by combining the first name with the last name and putting a space in between. Now, what's interesting here is that although we've declared the variable name, nm, to have type name, since we've now tested here, we know here, the compiler knows here, that name is string is true. And so we have narrowed the type of nm to be string. So this is okay. Even though name here is declared to be name and the return value is declared to be string, it's okay to return name here because we have checked that name actually is a string. And similarly here, we are accessing first name and last name, which you can't do on a string. You can only do on a structured name, but that's okay because name is a structured name or a string. We said here that it's a string, so the other case must be that it's a structured name. And so we know here that nm is a structured name, so we can access the first name and the last name fields. Okay, so we don't have, Ballerina does not have exceptions like in Java or JavaScript. Instead, we have error values. So it's a little bit more like C, but instead of having some using an error code or a string or a structure, we have a specific type of value called an error value that we use for reporting errors. And we use unions to describe the possibility the function either may return a non-error value or an error. So if I want to write a function that parses a string, that may fail. So I need to return, I may either parse it as an integer or I may return an error. And you just return the error value. So error here creates the error value and returns it. So in this case, I'm returning n, which is an int. In this case, I'm returning an error. And so the return type is int or error. If you want to have something that, if you have something more like a procedure that either that does something or returns an error, then the return type will be, so remember that nil, when you have a function that doesn't have an explicit returns, that returns the same as returning nil. So if I have something that either returns nil or error, that's the same as error question mark. So a function that, a procedure that does something, so a function like main, which either does something successfully or may return an error, that would have a return type of error, that can have a return type of error question mark. An error value includes, so it can include a message. It also has a, it can also has a stack trace, which will get printed out. So you can, typically the thing to do with errors is you return them back to someone who knows how to handle them. So I've said here that Ballerina requires ignoring an error. I'm going to talk a little bit about that, a little bit more about that later on. So typically when you handle an error, so how do you handle an error? Typically what you do is you get an error. So you're using, here we are calling a function that may return an error. We use is to see if it's an error. And then we use the usual control flow. We use the normal is construct, we use if. So basically the concept of error handling in Ballerina is is that errors are handled as part of regular control flow. And that's because Ballerina is a language that is designed for network programming. And when you're doing network programming, errors are normal things. And you want to be explicit about the control flow so that you know what's going on. It makes code a little bit verbose, but you can, by looking at it, you can tell, you know, where errors can happen and how the control can flow in the function just by looking at this code. But this is a very common pattern that you want to see if something's an error and return it, and if not, do something else. And so we have a shorthand for that. So we have this check operator. And what check does is see if the expression following it returns it's an error. If it does, it returns an error from the function. Otherwise, it returns that value. So if from bytes here returns a string, then that gets assigned to strut here. Otherwise, it will return from the function. So 90% of the time, when you get a function that returns an error, use check. That is what you want to do. That is mostly the right thing to do. I see a lot of people writing code that doesn't use check where it should do. Use check. There's not much you can do about it. Use check, return it, and let somebody who can do something interesting with it deal with it. But notice here that control flow is explicit. It may look a little bit like exceptions, but it's not. If this says check, you know that there's a flow of control from here returning from the function. So you always see where, if this threw an exception, there would be nothing that clued you into the possibility that this might return from the function. But here you can see this, and you can see explicitly that there's a possibility that you need to be aware of, that this function may return from the function. This call may result in return from the function. First of all, we need to understand that you can have multiple error types, which is what this slide I'm coming to does. So you can actually have different, types of errors. And one way you can, the most important way to distinguish types of errors is to use something called distinct. And what distinct does is says that these are errors, but they're different errors. And distinct is really a way to bring nominal typing into Ballerina. So Ballerina, I said, it uses structural typing normally, but languages like Java and JavaScript, and pretty much all the C family languages use nominal typing, where the type is part of the name. So the name is part of the type. So when you have, if I say class X, if I have two different classes in Java, which have the same bodies, those are two different classes. The name makes it a distinct type. So in here, we're saying that these are distinct errors. And when you do this,
when you create an error here, so I've got a distinct error type here, another distinct error type here, and when you create a distinct error type by giving the error type here, and this will then, and we've created a union here. So this will create an error value, which is, you can think of it as being tagged with a distinct ID. So this will be a different value. If you put X error here on Y error, you'll get a different value. And then you can use the is operator to distinguish between them. So I said we don't have exceptions, which is true, but we have what we call panics. We got this terminology, comes from Go, in fact, that we have what you might call normal errors and abnormal errors. Abnormal errors are things you really can't do anything about. It could be a bug in the program. Well, you can do that, you can fix your program, but they are errors where the normal reaction is just to give up. If your code has a bug, then the best thing to do usually is to just stop running the program, or maybe you'll stop running typically stop running the program. So abnormal errors are very restricted things. They're things like there's a bug in your program, basically, or you run out of memory. Things that you really just shouldn't ever happen. They're not things like you've got the wrong kind of input, or your network call didn't work. Things that happen and that programmers need to deal with, those are dealt with by normal error control. Things that really there's nothing you can do about are dealt with by panics. So with panic, if you find yourself trapping panics a lot, so there's a way to trap panics, which I'm not going to describe here, but typically if you have a panic, then your program will just stop and print an exception, and that's usually the right thing to do. But there is a way to trap them if you need them, but if you find yourself doing that, you probably should be using an error. Okay, any type. You can think of this as just being a big union. But one slightly thing that might trick you up is any type matches any value except for error. So it doesn't match error. And we want to be, this is because we want to be explicit about errors, and we don't want you not to allow error. So it's equivalent to a union of any basic type other than error. You can't actually do very much with any. Typically you have to cast it to another value. And the way you use an any value is typically to test what type it is and then do something with it. So that's coming on. So the reason why any is doesn't include error is we want it to be hard to actually this is a slightly different point. So we don't allow you to ignore return values. So if a function returns a string, you can't just say, I'm not going to look at the string. If it's returning a string because that's the important information that you're supposed to do something with. The only case where you can ignore the return value is when it's nil. So if you want to say, okay, I'm going to call this function, it's returning me a value, but I'm going to throw that away, then you can assign it to this special variable called underscore. And if you really don't want to, we don't allow, if this returns an error, we don't allow you to ignore the error. If you really, really want to ignore the error, because although this function says it can return an error, for some reason you know that it can't, you can use this really ugly keyword, check panic. And it's intentionally ugly because if you're doing this, there's probably something seriously wrong with your code. But if you know for whatever reason that this function cannot possibly return an error, even though it says it can, you can use check panic. And that will, if it does return an error, it will then panic. So let me talk a little bit about covariance. So this means that if I have an array of ints, I can assign it to an array of any's. And if you think about this from a sets of values point of view, this makes sense. An array of, so what's the type int mean? It means it's arrays where the members are ints. And this is arrays where the members are any. an int is an any, so right, the subset of the values allowed by this is a subset of the values allowed by that, so it's a subtype. So this should be okay, right? But this does actually create a problem because I've now assigned an array that can only contain ints to an array that only. Now, what happens if I try to assign a string to the first member of AV? This is okay, right? Because this is any. But whoops, suppose I allowed that assignment. My first, because this array is referred to by both AV, IV. If we allowed this to be modified to a string, then when I access the first member of IV, I will get a string, not an int, which would, not be what you expect from a statically typed language. So this has to be we allow, some languages don't allow this, but it becomes very inconvenient and it doesn't really fit into our structural typing module. So we allow this, but the downside is that this will get a runtime error. And this is actually the same, you can do the same thing in Java. Actually, Java will also give a runtime error with its built-in array types. So I think that's part of our overall error handling philosophy. No, sorry, it's part of not our error. That's part of our static typing philosophy. Is we do static typing, but we don't do static typing to the max. So we do enough static typing. Some languages are just very, very strict static typing and have very complex typing systems, and they catch a lot of errors. But the downside is they're very hard to use, hard to understand, and a little bit restrictive. And so we have a static typing, so we're not like a script. And some languages just don't have static typing at all because they just find it too inconvenient. We try to have a midway approach where we do have static typing, but we catch some errors at runtime so that the type system doesn't become either too complicated for people to understand or too constraining that it makes it inconvenient to write programs. So the way this works here is that when I create an array here, so it is an array of containing 3 values, and it also has something called an inherent type, which in this case is an array of ints. So this value says, and what the inherent type says is it constrains how the value can be modified. So this has an inherent type of, when you construct it, this type here determines what the inherent type of this is. So this will create an array with inherent type of array of ints. So when you try to modify it here, you will get, that will violate the inherent type, and so you'll get a runtime error. So what static type checking guarantees you is that when you read something from a mutable structure, you will get the right result. Writes into a mutable data structure can still fail at runtime in specific cases like this. And that's a trade-off we decided to make. Okay, so we have objects. I haven't talked about objects yet. We have objects. Ballerina is not an object-oriented language, but we do have objects. We use objects when you actually want the functionality that objects provide. What an object does for you is it bundles together code and data. And when you want that, you can use, we have an object type that you can use. So let's look at how you use an object. So you have some module that defines a class, and you use new on it, you pass some arguments, and then that creates you a value that's an object that belongs to the class, and then you can call methods on it, and you can access its fields. So it works pretty much like like JavaScript or Java. And if you define them, again, it's pretty similar to Java. You define a class. You can have private members, which means it's accessible only to the code in the class. And you have methods on it. And this, our constructor syntax looks like this. It's a special function called init. And you, oh yes, so we have self. So if you want to access a member, a field of the class, you use self to access it. Some functions use this, sometimes some languages use self, we use self. And then init, you have an init to initialize, you have an init method to initialize the fields. So if we go back here, the arguments to new here are passed here to the init function. So one convenient feature is that init can actually have a return type. So usually the return type is nil, but you can also return an error. And if it returns an error, then the new expression will return that error. So this means you can actually do something useful. A lot of things because we don't have exceptions, a lot of the time, if you actually want to do something substantive in the init method, there's a possibility that it will return an error. And so you need to be able to pass that through to the caller, and you can do that like this. So that means you can actually do real work in the init function. But note that the type of init here, you don't need to say it returns file, but that's what happens. If this succeeds, then the new expression returns file. If it fails and return an error, then the new will return an error. So we've talked about equals equals, and for arrays and maps and records, equals equals is deep. But there's also a concept of which I'll call identity, which does it refer to the same storage? Is it the same array? If I modify this thing, does it also modify this thing? Is it the same place in memory? And for that, we use trebles equals as in JavaScript. So for arrays, double equals will say, is it the same in the sense of, does it have the same members? Is it deep equals? Trebles equals means, does it live at the same place in memory? So for objects, you don't have doubles equals because their code, it doesn't make sense to do deep equals on code. What you have is treble equals. So trebles equals, basically something is treble equals, that means it's indistinguishable. So here, so this is doubles equals because they have the same values, but this is false because we have two, this constructs an array, this constructs another array. If you mutate this and mutating this, they're different things, both be mutated, not the same thing, not the same place in memory. So that would be false. And trebles equals is like for immutable things, trebles equals is the same as equals equals, except that trebles equals means that the values are indistinguishable. Is it the same value? So in some cases, there's one important case where equals equals is not the same as trebles equals for simple types, and that's for floats. So in IEEE, -0 and +0 are the same. IEEE floats, -0 and +0 are distinct values, but they're equals equals. We treat them, usually you want to treat them as numeric equals. So -0 and +0 are doubles equals, but they're not treble equals. Okay, const and final. So we have consts. Consts are a little bit like C++. They're compile time known value, and it's compile time known, it's immutable. We also have final, which is like in Java, that is not known at compile time, but you can't reassign it. So final string message, once you've assigned whatever load message does, you can't change it. But we don't know what value it has at compile time. So those are pretty normal. Enumerations. So enumeration is just a shorthand for a union of consts. So if I say enum red, green, blue, that actually is shorthand for defining 3 constants whose values are strings, and then making a type of the union. So this also illustrates that you can have what are called singleton types, and that's a type. So remember I said that types were sets of values. So you can have a type that contains 1 value. So this const red, it's a constant and it's also a type. You can use it as a type. So here I've defined it as a constant, but I can actually, I'm here using it as a type. So what type is it? Well, it's a type that contains 1 value. This here is a type that contains exactly 1 string, specifically the string red. And so this is a union. So this type has 3 values in it. Okay, so match. This is like switch in C or JavaScript. We're matching values here, not types. So on the left-hand side, so we have a left-hand side, and then we have an arrow, and then we have what you want to do in that case. And it tests each one in turn and until it finds one that matches. And if it doesn't match, then it doesn't do anything. So you can have a constant, yeah. So we've got a constant 17, we've got a constant true, you've got a string. You can also refer to a named constant. So if you have an identifier, that refers to a named constant. So is it equal? And again, here we're using equals equals to test things. We can have, so this syntax here, you can match several different, the choice of different ones. This means it matches 0 or it matches 1. And this case here matches a value of type any. So it's pretty much like switch. I mean, there are other features which we'll see later, but it's basically like switch. So sometimes it's convenient to not specify explicitly the type of a function. This is not a good example. So you could, instead of writing string x equals string, you can write var x equals string. There's not a lot of point in that because you know what it is. It's easy to write string, so that doesn't help you very much. But in some cases, it's a little bit more. If you've got a complex type, if you've got a record or something, it can be inconvenient to you sometimes forced to repeat yourself. And so var allows you not to repeat yourself. And in particular, it's often convenient to use var with for each, where you know, because you know that this is an array of strings, you know that this is a string. So this says infer the type of the variable from the context. And it works both ways. So you can infer here, we're doing new my class, so we know that x must be of type my class. You can also do it the other way around. If you've declared x to be of type my class and you knew something, well, you must be knewing my class. So it's a localized, this type inference is very localized, and the basic idea is to allow you to not have to repeat yourself. But don't overdo it. I see a lot of people using var because they can, but you've got to ask yourself when you're using var, is it making my code clearer and shorter? Like in here, you could just as well write string, and that's clearer. You know that S is a string. You don't have to, if you're reading the code, you don't have to go, what is SV? Oh, SV is a string, so S must be SV is an array of strings, so S must be a string. If you can without pain, without too much repetition, say what your type is, do so. Only do it when it really gets a little bit painful. Would be my advice. So we've seen a whole bunch of different basic types so far. We've seen objects, we've seen errors. We've also got functions. Functions are a kind of value. We have functions are values, what people call first-class functions. So you can pass functions around like values. And when you do, a function isn't just code, it's also the context in which the code is called. So it's a closure, which means that it remembers what each local variable refers to, and that is part of the value. And so we support, and this works very much like JavaScript. we support the usual. So here we're having, so this is an interest, this is a good case of where it would be painful to not have var. So here I'm inferring the type of var is a function type. This is the function type. It's a function, has an integer argument and returns a Boolean. And I'm constructing a function with that type. And I'm assigning it to is odd. If I had to write here, I could not have var by writing instead of var this, but that would be pretty repetitive. And so this is a nice case where it really is very convenient to have var. And once we have is odd and is even, we can then, and so here's that, so here's another one, is odd and is even. So we can also write this, when you write a function like this, it's also, you don't have to write it like this. When you write functions like this and write functions like this, they're the same thing. And when I refer to is even here in an expression, I will get a value of type function. And so I can write the type of function here like this and give it a name, int filter. So I can have a variable here, f, of type int filter, and I can refer to the function here that I found using the normal syntax, and that will give me a value of type function. And then I can, suppose I've got an array of numbers, we have the usual, the lang.array, there's an array langlib module that has a bunch of different functions on arrays, and one of them is filter. And so filter takes an function value as a parameter and gives you the things for which the function evaluates to true. So here I've assigned is even to a variable type f, and I pass that into the filter function, and that will give me the even numbers. And then we also got this syntax here, which is for anonymous functions, where here, again, this is a kind of type inference. I'm inferring the type of the, so here we're not specifying the types of the parameters or return types, but I'm doing filter to an array of ints. So I know that the type of the function, the argument type for the function is int. So here I can infer the function type that I expect, and I don't have to repeat I could use this form. I could use this form, but that's very inconvenient. So instead I infer the type of the function from the declared type. So I infer the type of the closure from the declared type of the filter function and the declared type of the things applied to nums. Again, this works pretty much like, this should look very similar to, this looks very similar to JavaScript, for example. We also have, asynchronous function calls. So you can start so what start means is call this function, but don't wait for it to return. You'll get a value of type future. Again, future is another basic type. And you can then wait for it. Wait can return an error, so you use check. And so I've started two functions off, and then I'm gonna wait for both of them and get the value back. You can also wait for them at the same time, so you don't have to do this. Waits for both. This waits for both of them to. Sorry, that's not right here. That should be x1, x2, I think. Sorry, that should be x1. That should be x1, x2, not f1, f2. That's a mistake. So you've waited for them, and then you can. No, that's not right. Sorry, that should be. So I've called them f1 there. So that should be. Well, it'd be easy to say x1. Sorry, this should be x1, x2. Here's the easy fix. This should be x1, x. No, wait a second. I'm myself confused here. So there's the. So we also have something like the equivalent of Javadoc, where instead of using // we use this hash, and within this hash mark, you use markdown syntax. And then we have some particular conventions of how you use Markdown. So this is the convention for how you document integers and how you document the return value. And then there's a tool in the Ballerina platform that will turn this into like the Javadoc tool, that will turn this into pretty hyperlinked documentation. And then we have an annotations feature, which uses @ So really, we have two kinds of metadata that you can add to a function, and these types of metadata both go before the function. There's @ which is the annotation feature, which is general structured one, and then there's hash, which is a specific for documentation. So @ has a tag, and then it has a record that you can put after it, and this is tagging this function with this and applying this annotation here to this function. And this one here is putting another annotation on a start. This is saying something about how you can schedule this feature. So unprefixed tags, here we see unprefixed tags, and they refer to things that are defined by the Ballerina platform. You can also define your own annotations, and they would use a prefix to refer to something defined in a module. And yeah, I think that's it.